At this point, we now need to start getting into more integration techniques. We saw some of the downfalls of not being able to integrate certain functions in the previous unit when we were looking at applications. So now we need to really hone our skills for integration. So we have all the things we've talked about so far throughout Calc 1 and Calc 2. The basic integration rules that we've learned of how to integrate certain types of functions, the major technique of U substitution, and we have some of the little tricks we've learned along the way, like, say, completing the square before you integrate to help turn it into a possible integral we can work with. So this whole unit is all about learning more techniques to give us a wide array of possibilities for integrating functions. And the goal is that by the end of this unit, we should be able to integrate most any function that we come across that is able to be integrated. All right, so the technique we start with is something called integration by parts. It is the closest thing you will ever come to a product rule for integration. So we don't have a product rule for integration. We don't have a quotient rule for integration. This is what makes integration mostly the most difficult as compared to differentiation. Differentiation, you have a rule for every different type of function. And as long as you can apply the rule, you do it, you're done. We have very limited rules for integration in that we don't have a standard way of integrating every single product. We don't have a standard way of integrating every single quotient. And so that's where we have to get into these techniques, and U substitution was one way to do that. So this is the closest thing you will come to a product rule for integration. So a way of integrating a product. Now, it doesn't work for every product, okay? But it is essentially based off of the product rule for derivatives. So let's look at the product rule for derivatives before we introduce what integration by parts is. So you have your product rule for derivatives. So let's say I have u times v, and I want to take the derivative of that. So use prime notation there. So what I would do is I would take u times the derivative of v plus v times the derivative of u. Now what I'm going to do is I'm going to rewrite this as u times dv plus v times du, where dv represents a derivative of v and du represents a derivative of u, and this would all be with respect to the variable we're discussing. We could also write this as dv dx du dx if you want to say that all this stuff is a function of x. We can do that as well. All right, so then what I want to do is I want to integrate both sides of this equation. So I have this, and I want to integrate both sides of this equation. So what I'm going to do is I'm going to multiply the dx through to the other side. So I'm going to do the integral of the derivative of u times v with respect to x. Then I'm going to do the integral of u dv plus the integral of v du. Well, if you're integrating the derivative, these just cancel each other out, so you get u times v. And here, you don't know what these functions are, so these will stay u dv plus the integral of v du. Then what I'm going to do is I'm going to move this to the other side of the equation by subtracting it, so I'll have u times v minus the integral of v du equals the integral of u dv. This is exactly what you see listed here. So that's where it came from. Now, how is this helpful? Okay. First, this is the integral we would begin with. Okay? This is where we're going to start. And in this integral, you have two things multiplied together, u and dv. Remember what was dv? dv was the derivative of v. So v is a function of x. U is a function of x. So I have two functions here multiplied together. One is the original function u, and the other is the derivative of some other random function v. Okay. And this is the thing I want to integrate. So if I want to integrate this entire product, what this formula tells me is that this is what the answer should look like. Now the answer has a couple of components to it. We have u, we have v again, and we have du. So if we identify these two pieces here, we have u and we have dv. What we would need to do is know what u is and place it here, which we would just know that by identifying it in the original integral. But we would also need to know what du is. Well, how would we find du if we know what u is? Well, we would have to take the derivative of that. And once we do that, we'll place it here. And then we need v. Well, we have dv from the original integral. We just identify it out of the original integral. Well, how would we find v? Remember, dv is the derivative of v. So if you have the derivative and you want to go and find v itself, you would have to integrate. So we differentiate here, we integrate here, and we get these four components: u, dv, du, and v. And so then I would place that v that I found here and here, and this is what the answer for my integral should look like. Now, the problem with this is that you're answering an integral here with another integral. The reason for this, and the why it works, I should say, is that this resulting integral should be easier to evaluate than the original integral you were trying to work with. And if that's the case, then you could do this integral and therefore complete the entire answer. I know that sounds like a lot. It'll make more sense when we start looking at problems. But it's all about, let me erase some of this so you can see it better. It's all about looking at your original integral and identifying the two components of that integral and saying this piece is u, this piece is dv. I will differentiate to get du. I will integrate to get v. Once I have these four pieces, I have to know how to put them back together. And then once I put them back together, and the way you do it is a fairly simple pattern: u times v minus v du. Okay? So if you set up this square, u times v minus v du is the way you do it. You create your answer, and you integrate the final piece. So here we go. Let's do this, and I'll go up to these guidelines. So integral of x e to the x dx. So this is what is going to take you some time, is how do I know what u should be and what dv should be? I'm going to tell you that u in this case should be x, and dv should be e to the x dx. Now why we'll explain in a moment. So I should find what du equals, which would just be the derivative of x, so dx. That's just your basic like u substitution. This is nothing new. Here's a little bit different in that now we're going to integrate e to the x dx. So that's going to give me e to the x. Notice the dx component of the integral goes here. It always goes with the dv component. And so I then have to apply integration by parts, which remember, if we have the integral of u dv, sorry, let me make sure my u's look like u's, u dv, it should be u times v minus the integral of v du. That's our setup. So I have to do u times v, so that would be x e to the x minus the integral of v du. So that would be minus the integral of e to the x dx. Now notice what we get in this integral. It's just the integral of e to the x dx, which we actually already did from here to here. So it created this integral, which is a little bit more complicated, created an integral that was a little bit easier to do. And so we end up with x e to the x minus e to the x, and then throw plus c on the end, And there you go. Now, a couple of things need to be said here. One, why did I use integration by parts on this in the first place? That's the one thing you're going to have to start getting used to is when should I apply integration by parts? Well, let's look at this. X e to the x dx. Do I have any other options? Well, again, really, your only option you have in terms of a way of integrating functions that are not already in a basic form is largely substitution. Well, there's no substitution going to go on here. If I just let u equal x, I'll just get the same thing again. U equals x, du equals dx, and so I just get a bunch of u's everywhere instead of x's, but it doesn't really change anything, so that's no good. All right. Well, what if I let u equal e to the x? Well, du is e to the x dx. Well, I only have one e to the x. I don't have an extra e to the x, and I still have this other x here, so that doesn't work. And you see really quickly, like, substitution is not going to happen here. Okay. So then you go, all right, well, why should I use integration by parts? It's a product. Okay. Not every product will use integration by parts, but the fact that this is a product, integration by parts should be something you think about. Now, why did I use u to be x and dv to be e to the x? Well, a couple of things, and this comes into the guidelines for integration by parts. First, it says, try letting dv be the most complicated portion of the integrand that fits a basic integration rule, and then u can be the remaining part. Well, I don't know that x or e to the x dx is complicated, so I don't know that that really fits as much. And it says try letting u be the portion of the integrand whose derivative is a function that's simpler than u it was itself. Well, I think that one really applies here, and dv can be the remaining. So if you think about it, x is your u, and the derivative is just 1 dx. Well, that's definitely simpler, right? So by default, then, e to the x dx becomes my dv, and we go from there. The way I usually look at it is when I'm trying to determine my u and my dv, is I say, well, I'm going to have to differentiate this one and integrate this one. Is there one of these two functions that's easier to integrate or easier to differentiate? And in this case, no. I mean, x is pretty easy to both integrate and differentiate, and e to the x is pretty easy to both integrate and differentiate. So it doesn't really apply too much here. So then the second thing I do is I basically look at what this one said here. If I was to differentiate one of these, would it become simpler? And the answer is yeah, well, the x does. The e to the x doesn't, just keeps staying the same. So that's where I decided, okay, there's my u, and therefore the other piece is my dv. The more of these you do, the better you get at that, and you start to see similar things happening over and over again. Sometimes you won't know what u and dv should be, so you just try. You place something in the u spot, differentiate, place something in the dv spot, differentiate it, or integrate it, and see what happens. And sometimes until you write it down, you don't actually see how the problem's going to work out. And sometimes you'll pick the wrong ones. You'll pick the wrong u and the wrong dv, and you'll see what happens is the second integral that you have to now do is worse than the first integral, in which case you know I probably picked the wrong u's and dv's. Let me try and switch it up. Or maybe you go, well, integration by parts is not even an option for this problem. Because remember, not every product is going to be done using integration by parts. This is the trick of integration. Because if I gave you this example, 2x e to the x squared dx, and I said do this. Well, that doesn't look too different than the example we just did. But it is not an integration by parts integral. And this is why integration is tricky. This is just a simple u substitution. U equals x squared, du is 2x dx. And the reason why this happens and why I should notice this is I see a pattern of function, and that function's derivative is sitting inside the integration. So what am I going to do? I am going to write this as e to the u, And then 2x dx, which is all this here, is just du, and I could integrate this. So understanding integration by parts is used for products, but not every product will be integrated using integration by parts is a key to getting good at this. Here's another one. There's a problem with this in that there has to be an x here. You have to take the natural log of something. You cannot take the natural log of dx. It's just a typo, but should be noted. So let's just cross this out and rewrite it. So the integral of 3x to the fourth times ln of x dx. So we got to decide which one is u and which one's dv. So now think about this. Is it easier to integrate or differentiate one of these two functions? So if we look at 3x to the fourth, I can integrate it or differentiate it fairly easily. Log x, however, the only thing I can do is differentiate it. We have yet to discuss how to integrate log x. We will in a short bit of time, because today we're going to learn how to do it, but we haven't done it because it's not easy. So u has to, by default, be ln of x. dv is 3x to the fourth dx. You could pull this 3 out as a constant multiple. I like to leave it in when I do integration by parts. That way I don't have to worry about distributing it later. You could decide either way. du would be 1 over x dx. v would be 3x to the fifth over 5. Remember, you're integrating. So then we would get u times v, this times this, minus this times this. So u times v would be 3x to the fifth over 5 times log x minus the integral of 3x to the fifth over 5 times 1 over x dx. Remember, our hope was that the second integral would be easier to do. You might look at this and say, oh, it doesn't look too easy, but actually it is, right? This x here and this x here, we can cancel, so this will become x to the fourth. And all you really have is a power rule integral. So if you look at it, we have 3x to the fifth over 5 ln of x minus the integral of 3/5 x to the fourth dx, 3/5 being a constant multiple. And all we're really doing is integrating x to the fourth. So in the end, 3x to the fifth over 5 ln of x minus 3 over 25 x to the fifth. Now over 25, because this would be x to the fifth over 5 with this extra 5, that's where the 25 comes in. Throw a plus c, and there is our answer. Pretty easy, as long as you do this correctly, right? If we didn't pick the right u and dv, it doesn't work out. So you need to get practice on how we do this, and the more of these you do, the better you'll get. So now it's time to do this integral, the integral of log x dx. Okay, we've talked about it a couple times now in previous lessons and today. And so now what we need to do is figure out how do we integrate it. Log x is a basic function, right? It's one of our basic functions. We should know how to do the integral of a logarithm. But we haven't up to this point because we need integration by parts. Now, I've been telling you through this lesson that integration by parts is used for products. And you might look at this and say, well, there's not a product here. It's just one function. It's log x. However, log x is multiplied by dx. So in a way, there is a product here. And so I want to try integration by parts on this one. For the same reason as the last example, u has to be log x, because we don't know what the integral is. That's the whole point of this question. dv, the only other option for dv is the dx, is the only thing that's there. Think about it as like 1 dx. So then du would be 1 over x dx. V would be x, it's the integral of 1, And then your u times v minus v du would simply be x ln of x minus the integral of x times 1 over x dx. Well, these two will cancel each other, so you really just have the integral of 1 again, and so you end up with x ln of x minus the integral of 1 is x plus c, and you're done. Okay. And that's how you're going to integrate the log of x dx. Now, my suggestion is that you commit this to memory along with your other basic functions that you should know the integral of. It's one of your common functions, so knowing what the integral is important. So when I've been talking about creating a set of index cards as flashcards, this is one of them you should add to the list. Because if I gave you this integral, the integral of 2x plus 1 times log of x squared plus x dx, and I said do this integral, you could get this done simply by doing integration by parts on this whole thing. However, if I just did substitution and I said u equals x squared plus x and du equals 2x plus 1 dx, this would simply be ln of u du integral. Here's my du, here's my u, and it should be u ln of u minus u plus c. Throw in what u was, which was x squared plus x, and you have your answer. It makes it a heck of a lot easier to do if I knew this general rule for integrating a logarithm. So I think it's worth committing to memory, considering this is one of your most basic functions. But now you know how to integrate a logarithm. This next one is the same thing. We haven't integrated an arc, sine, or tangent, or secant function yet either. Right? We haven't done integrals of any of the inverse trig functions. We've done integrals where the answer is an inverse trig function, but we haven't done something like this. So, same idea. Now, I also threw in this definite integral component to it, which is just something we worry about at the end. We got to evaluate this thing. But the main point of this example is to be able to figure out how do we integrate the arc sine. So we have two pieces here. The arc sine of x is the one and the dx is the other. I can't let dv be arc sine because I don't know how to integrate it. That's the whole point of this problem. So u is going to be arc sine. I know how to take the derivative of arc sine. And dv is going to just have to be the dx. So du is going to end up being the integral of derivative of arc sine, which is 1 over the square root of 1 minus x squared dx. And v is going to be just x again. So what do we end up with? We end up with u times v, which is x arc sine x, minus the integral of v du, which is x over the square root of 1 minus x squared dx. Now remember, we had this definite integral component. There's two ways to do this. This whole thing is our answer, right? Whatever this ends up being, we still have to finish this piece. So the whole thing should be evaluated between 0 and 1. So there's two ways to do this. One notation would be to put a line here, so you remember to evaluate that part between 0 and 1, and then place a 0 and 1 on this integral. I think that's overkill. I don't like doing it that way, but you can do it. But that reminds you that this also needs to be evaluated between 0 and 1. The other option for notating this that I like better is to just put a bracket on the end here with a 0 and 1. And remember, okay, well, that means the whole thing is going to have to be evaluated between 0 and 1. Okay? Put a bracket on the other end, too. So anyway, we still have to finish this. That's going to have to be done. That integral is going to have to be done using substitution, in that I have a u to be 1 minus x squared. I have a du to be minus 2x dx. I have the x dx, just not the minus 2. So I'll move that over. So as far as this integral goes, if I kind of take it off to the side, I have a minus outside. I have my x dx becomes du over minus 2, so that'll become a plus 1/2, and this becomes square root of u. Well, square root of u is the same thing as u to the 1/2, but that's in the denominator, so then I bring that up. So then I end up with 1/2 the integral of u to the minus 1/2 du, and therefore that becomes 1/2, add 1 to the power, so we get u to the 1/2, and then divide by that means multiply by 2, which cancels these. So the integral is u to the 1/2, where here was my u. So if I place that in this problem, I have x arc sine x plus because I already initiated the negative into the problem, u to the 1/2, which was 1 minus x squared to the 1/2. Evaluate that whole thing between 0 and 1 now, and we're good to go. But ultimately, this is what we were trying to get to. This is the integral. And so you had to look at integrating this piece, which is not necessarily the easiest, but you would have to use substitution to get the answer. So if I plug in 1, I get 1 arc sine of 1, plus plug in 1 here, I get 0, minus, if I plug in 0, I get 0, arc sine 0, minus 1, because this will be 1. Well, arc sine of 1 can be evaluated. Arc sine of 0 is 0. So arc sine of 1, what angle when you took the sine of it would you get 1? And that would be pi halves. So pi halves minus 1 is the answer.
So we've seen that integration by parts yields another integral within the formula. Well, what if that other integral was also an integration by parts integral? Well, then that would yield another integral, which could then be an integration by parts integral, and so on. And so what could happen is that we could have to use integration by parts a repeated amount of times. We might have to apply it multiple times in a given problem. And so here's an example of that. So if we look at this function, it's a pretty common example that we would use for something like this. It's going to have to be done by parts. It can't be done by simple substitution. The u and the du, while you might say here this and this are in some way related through derivatives, they're in the wrong location. So it's not going to work in terms of substitution. So if I did u to be x squared and dv to be sine 4x dx. Now, why did I do that? Well, first off, I look at the two functions and I ask myself, is one of these easier to integrate or differentiate? And the answer is no. I think x squared I can integrate or differentiate really easily. Sine 4x I can integrate or differentiate really easily. So it's not like it's going to be easier to do one or the other for either function. So the next thing is, which one becomes simpler if I were to integrate or differentiate it? In this case, x squared is definitely going to become simpler because it becomes just 2x dx, where sine just keeps cycling back and forth between sine and cosine. So in this case, I would have the integral of sine, which would be minus cosine 4x over 4. So then what I'm going to do is create my u times v minus my v du. And so what I end up with here is minus x squared cosine 4x. This is jumping all over the place. Let's see if we can fix that. So x squared minus x squared cosine 4x over 4 minus the integral of v du. So since this already has a minus, that'll turn this into a plus, and I end up with 2x over 4 cosine 4x dx, which I can simplify to just 1/2. But I look at this and I go, okay, now this is the integral I'm going to have to work with. Well, in a way, it's not that different from the original integral in that I have x to a power, so x to the first power. And in this case, I have a cosine 4x instead of sine 4x, but don't sine and cosine essentially act the same way within integration? The way we integrate each one is very similar. And so this integral is really not that different than the original. I don't have anything in terms of a u du or simplification with u substitution that's going to work. So what I have here is actually another integration by parts integral. So in this case, I'm going to let u equal, again, the x to the power part. So I'm going to call this x over 2. I'll make that my u. And my dv, in this case now, will be cosine 4x dx. So du would end up being just 1/2 dx, and v will now be sine 4x over 4. So I still have this minus x squared over 4 cosine 4x from originally, plus, because remember this changed to a plus, another u times v, which in this case would be x over 8 sine 4x, minus the integral of v du, which now would be sine 4x over 8 dx. All right, well, here's where integration by parts is now done. We have to do this integral, but this is no longer an integration by parts integral because there's no more x, there's no more power function out in front of this trigonometric function. It's just the sine. That's the only thing we're integrating. The 8 here is a constant multiple, so it's the integral of sine 4x, which we already did back here. So once we integrate that, we end up with negative x squared over 4 cosine 4x plus x over 8 sine 4x minus negative cosine, so that we become plus cosine 4x over 32. Over 32 because it would be over 4 with the extra 8. That's where the 32 comes from. Throw a plus c on the end, and there's your answer. So in this case, we had to do integration by parts twice, right? We had to do it here, and we had to do it here. Sometimes you might have to do it 3, 4, 5 times in an integral. So we have to look at some of these examples. Now, there's a way we can speed this problem up. This doesn't always work, but there is a way to speed this up, and it's something called the tabular method. So notice, u was x squared, and then the derivative of that is the next u, and so on. And the same thing with the dv. dv is sine 4x, and then the integral of that is the next dv, and we go from there. So what we're going to do is we're going to say, here's u, here's dv. And my u was x squared, and my dv was sine 4x. And this is a shortcut, so I'm not going to write the dx anywhere. Again, we're trying to make things easier. Anytime you do a shortcut, you cut things out that, make it easier. So what I'm going to do is I'm going to differentiate my u until I get 0. So 2x to 0. Then I'm going to integrate my dv the same amount of times. So we get minus cosine 4x over 4, then minus sine 4x over 16, and then positive cosine 4x over, what would that be? 4 times 16, 64. Okay. All right. Now what we're going to do is we're going to match up our u times v, right? And the next integral, this will be the next u and the next v, and so on. Because that's how we create these pieces, right? This is u times v, then this is the next u times v, and then this is the next u times v. Well, really, it's just the integration that we did at the very end. And then the last thing we have to do is introduce the fact that every time we do an integration by parts, we subtract the integral. So the first u times v is plus, and then we're going to subtract the next one. And then we're going to have a double negative, which is going to turn the next one into a plus, because we're going to subtract a negative, and so on. So we have to keep switching out the signs here. alternating them, plus, minus, etc., until we get to the end. Anything after this is just going to be 0 times 0 times 0 times. And here's our answer. So if you look at the first one, x squared times negative cosine 4x. That's what we have down here. Then the next one is 2x times negative sine 4x, but with an extra negative because it's being subtracted. So these two negatives turn into a plus. The 2 and the 16 turn into just an 8. So we have x sine 4x over 8. That's what we have here. Then the next one is a plus. 2 times cosine 4x over 64. Well, the 2 and the 64 give me the 32. So positive cosine 4x over 32 is there. So this sped things up considerably, but you have to understand where it comes from this piece, as to why it works. The best time to do your what we call tabular method is when your u is one of these power functions, because you differentiate it till you get 0. And those work out the best. What I would suggest is that you only do it for these ones. Technically, we can do tabular method for a lot of other integration by parts. It gets fairly complicated. You're better off writing out integration by parts for the other ones over and over again, but sometimes we can do the tabular method.
Here's another example where we're going to use tabular method. It's not that different than the last one. Here I have a power function and a cosine, versus the last one was a power function and a sine. So if I say u is x cubed and dv is cosine x, let's differentiate this one. 3x squared, 6x, 6, 0. And then let's integrate this one the same amount of times. So sine x minus cosine x minus sine x, and then back to cosine x. Now we're going to match them up on the diagonal, because what we're really doing is matching up. This is u times v, and for the next one, this is the next u in the v, this is the next u in the v, etc. Okay? And then we got to introduce the pluses and minuses. So every time we do integration by parts, we subtract. So the first one's always positive. We're going to subtract out the next one. Then we're going to subtract out a subtraction so that it turns back to positive, and then negative, etc. So all this means is I'm going to be multiplying by positive 1 or negative 1 times this product. Okay? So we put it together, and what do we get? Well, we'll get x cubed sine x. Then this next one here will be 3x squared times a negative times negative cosine. So the two negatives actually end up giving me a plus 3x squared cosine x. And the next one is 6x times a positive times the negative sign, so that would be minus 6x sine x. And then the final one here is 6 times negative 1 times cosine, so minus 6 cosine x. Throw a plus c on the end of that, and that whole thing is the answer for that integral. And done fairly quickly, and really not that difficult. If you had to do integration by parts, you would have to do it 3 times to get through this one. The final integral not being integration by parts would just end up being this answer. But nonetheless, you can do it. Again, only suggest you do it when your u is this power function. So the best ones to do tabular method for would be x to a power times sine, x to a power times cosine, Sorry, my pen's not working right now. Anyway, so x to a power times sine, x to a power times cosine, and x to a power times the exponential function. Those three that you see down here at the bottom are the best ones for you to do integration by parts using the tabular method for. So with the previous two examples, we've seen instances where you're going to have to use integration by parts multiple times in one problem. But is there a possibility that you would have to continually use integration by parts over and over and over again, and it never stops? Well, the answer is yes. And this example is one of the most common examples you'll ever see for this type of instance. Okay, open up any calculus book, and this example is the prime example that they use to see a situation where integration by parts will have to use multiple times, and it could never end. Now, we don't just keep doing it forever. There's a way to rectify this problem, and we'll see it in this example. But this is the prime example of that. So, first off, what I'm going to do is I'm going to rewrite this integral. I'm going to write it as the integral of secant x times secant squared x dx. Now I do that because it's still secant cubed. But the reason why I do it that way is secant squared is a very easy integral to do. And secant itself isn't too bad when it comes to taking the derivative. Okay? So this is what I'm going to do. I'm going to say my u is secant x. My dv is secant squared x dx. So my du is secant x tan x dx. And my v is the integral of secant squared is tan. So if I did u times v minus v du, I would get this. So the integral of secant cubed x dx equals secant x tan x minus the integral of secant x times tan squared x dx. Now tan squared because I have a tan and another tan. Alright, so now I want to do this integral. Well, in order to do this integral, I'm going to rewrite it. And I'm going to rewrite it using the Pythagorean identity for tan squared. Tan squared x equals secant squared x minus 1. So I'm going to use that here. And I'm going to get secant x, sorry about this, secant x tan x minus secant x times secant squared x minus 1 dx. Now, I did that because now I can distribute this secant into here. And so I'm going to keep writing this over and over again. Secant x tan x minus, this will now become secant cubed x minus secant x dx. Now something interesting happens here. The thing that's interesting that happens here is these are subtracted, which means I should be able to integrate this separate from this. And if we have to integrate the secant, we can do that. That's a fairly common integral to do, so we should be able to do that. This negative could also be distributed in here and here. So where I would be at this point would be that secant x tan x minus the integral of secant cubed x dx plus the integral of secant x dx. So if I can evaluate this, no problem, I should know what that is. But look at this one. That's the same integral we started with. So if I'm going to do that integral, I should start off by doing it with integration by parts and then do this, which will then essentially give me this piece, which will turn into this, and another secant cube is going to pop out. And I'll do the same thing all over again, and over and over and over. It'll never end, right? Never. I could just continue doing this, and the same thing's going to keep developing, and it's going to get bigger and bigger and bigger, and it'll never stop. Well, I don't want to do that. I don't have forever to finish this integral. So what I want to do is figure out, how do I get this thing done? How did I get the same integral I started with to pop back up in here? Well, it's just something that happens with integration by parts, but now how do I deal with it? Well, how I deal with it is I stop. I don't actually evaluate this integral. I leave it. When I realize that it's the same as the integral I started with, I leave it. I'm going to evaluate this one over here. Okay? What I'm going to do is, remember, this is an equation, and this side of the equation is secant cubed x dx is over on the left, and all this is on the right. I'm going to just use a little bit of algebra, and this is being subtracted, I'm going to add it to the other side. Well, if I add it to the other side, I have one of these secant cubed x dx integrals over here, and I'm going to add another one of those over there, so now I'm going to have two integral of secant cubed x dx on the left-hand side. On the right-hand side, I have secant x tan x, plus the integral of secant x is the log of the secant x plus tan x. Don't worry about the c yet, we'll throw plus c at the end. And so we're at this point. Now this is almost what we want. This tells me what 2 times the integral of secant cubed equals. That's not what I want to know. I want to know just what the integral of secant cubed equals. That was the original question. So all I really have to do is get rid of that 2. Well, it's still easy. Divide both sides by 2. So now finally you get that the integral of secant cubed x dx equals 1/2 times secant x tan x plus the log of secant x plus tan x. And now throw a plus c on the end there, and you're good to go. So, something to think about. If you're ever doing integration by parts, and the original integral happens to show up within your integration, don't continue down that path. Finish off everything else, like here we finish everything else, but don't do anything more with this piece. Stop. Stop, move it to the other side with the original integral. You're just going to have some multiple of that original integral over there. Then you divide out that multiple, and you have the answer you want. Here's another example of one that's going to repeat itself. And the original integral is going to come back again. This is a really nice integral in that you can't mess up with what you decide u and dv are going to be. You could let u be e to the x, you could let u be sine x, dv, either one, and you will not mess this up, because either way you do it, you will get the answer for this integral. So what we're going to do is we're going to say this is u and this is dv. Because when I look at this and I try to decide which way I should do it, e to the x, pretty easy to integrate or differentiate. Sine x, pretty easy to integrate or differentiate, so that doesn't help. Neither of which is going to become simpler if I integrate or differentiate them, because they're just going to keep oscillating back and forth, which is the reason why the original integral comes back again. And so, this one, it doesn't matter how we assign our u and our dv. Also understand that why are we going to use integration by parts for this one in the first place? Well, it is a product, okay? That's not the only reason. It's a product, and we really don't have any other choice. There's no type of u substitution that's going to work. This doesn't look like any other simple integral that we could relate it to. So we're going to try using integration by parts. Again, sometimes you try something and it doesn't work, and that's okay. So you try something else. And by having all these things that we've talked about up to this point as options for how we can integrate, you should have at least a few things that you could try for each integral, one of which should definitely work. All right, so here's where we're going to assign it. Our du is going to be e to the x dx. Our v is going to be the integral of sine, which is minus the cosine x. Okay? So we're going to get u times v, which is going to be minus e to the x cosine x, minus the integral of v du, but since this has a negative with it already, it's a plus e to the x cosine x dx. So I'll just bring that negative out with the other negative. All right, now I'm going to do integration by parts again. U dv. The key here, and the key to a lot of these when you're going to do integration by parts multiple times, is you don't want to change what you do with integration by parts in terms of how do you assign your u and your dv. So the idea is, all right, if I let u be e to the x the first time around, I'm going to let u be whatever came from that the second time around, then the third and the fourth. And the same thing with the dv. The dv was the sine. What came from the sine was the cosine, so that's going to be my dv the next time around. And you want to try and keep to that pattern, because if you start switching it up, if I then said this time, here's my dv now, and here's my u, all I'm going to do is undo the step I just did and kind of circle back to where I was. And it's not going to work out nicely. So once you pick your u and your dv, and you're going to do it multiple times, be consistent. All right, so this one's going to be, what, sine x. So I'm going to have still the negative e to the x cosine x from the beginning, plus, now the next u times v is going to be e to the x sine x, minus the integral of v du, which would be e to the x sine x dx, which you notice is the original integral that we started with. So what I'm going to do is I'm going to move this to the other side by adding it. So if I add it, there was one here, I'm going to add another one, so now I have two of them. What's left on the right hand side is this minus e to the x cosine x plus e to the x sine x. So then I just have to divide by 2, and there's my answer. Throw plus c on the end for good measure. So the integral of e to the x sine x is equal to this. Okay? Again, I don't want to keep going down this road. If I keep integrating this, then the same thing that we just did is going to happen again, and this is going to pop out again, and then it's going to happen again and again and again, and it'll never stop. So stop the madness. Once you get the original integral, stop, move it to the other side, get some multiple of that integral, and then divide by that multiple. So here's a basic summary of some fairly common integration by parts integrals and how you should assign your u and your dv. Now this doesn't cover all of them, every single integral you're ever going to see, but this is some fairly common ones. So the first one is a power function times an exponential, a power function times sine, a power function times cosine. In which case the power function is u, the dv should either be the exponential, the sine, or the cosine, and these are great ones for tabular method. Okay. Another ones you'll see is a power function times log, a power function times arc sine, power function times arc tan. In this case, you're going to reverse it. Your u is going to be the sine or the arc sine or the arc tan, and your dv is going to be the power function. The reason for this is that these are easier to differentiate than they are to integrate. So that's why we choose those to be our u's. Third case, exponential times sine or exponential times cosine. We just saw an example of that. These are the ones where it really doesn't matter how you do it. You'll be able to get them done no matter which way you assign your u and your dv. These are also going to be the ones where the original integral pops back up again. Your book says you let u be the trigonometric function and dv be the exponential. The previous example, we let u be the exponential instead. It doesn't really matter. What would matter is that your answer may look a little bit different depending on how you assign these. But that doesn't mean it's a different answer. It's just a different form of the answer. And so if you do this, you may, if you don't follow this order for u and dv like we did in the previous example, your answer from what you get in the homework to what you see in the book will be different. So if you want to ensure that you're going to get the same answer the book is getting when it comes to homework problems like these, this is how you should assign your u and your dv. But really, in the long run, outside this class, it doesn't matter. These are the ones where, no matter how you assign it, you'll be able to get through the problem. So there's your integration by parts. Probably one of the most important integration techniques you will ever learn, aside from U substitution. U substitution by far is the most important integration technique that you'll learn, but integration by parts is probably the next most widely used method of integration aside from U substitution. So it's very important that you get this down.